Okay. So today we will continue with the tutorial we started yesterday. For those that weren't present, you can find these slides here, this link. Just a communication from my side, I need to leave sharp at 1, actually 5 to 1. So yes, I hope we will see what we can do. And if you have questions, please ask in time. Okay. Okay, so let's continue with the numerical methods behind all lattice QCD calculations and what you saw with Dina. This is something you already seen in our slides, and it's at the basics of all the calculation we do. So yesterday we saw for the example of a correlation function, okay? And all the calculation we do at the end of the day boils down to measuring correlation functions on the lattice, right? Because what we said is that we made what we put in our simulation on the lattice, it's really only the vacuum, right? So all our gauge fields are just sampling the vacuum, and then you need to put inside particles. And the only way to measure observable, it's via correlation functions. Why this is very important? It's very important because when we measure the correlation observable, for instance, separated in time, this correlation at leading order, it's given by the matrix element of the transport matrix up to the power t, as many times we separate, where t is the distance between the two. And I'm saying a leading order because being on a lattice with periodic boundary condition, then you have always finite size effects here, okay? So there's two, like we saw yesterday, to correlate to something measured between 2 points, it's at leading order the distance between the two plus periodicity effects. Okay, so these are all these dots. And if we expand these, the transport matrix for us, it's the exponential of the Hamiltonian, and you can insert a complete set of states of your theory, and you can write the correlation functions in terms of a series of exponentials. So it's something that always decays exponentially with the energy put here at the exponential. And from here, you can understand that what you can really measure easily are only ground state matrix elements. So the ground state is the one with the smallest energy. This is the ground state. And it's the one you can measure easily because it's the only one that survives at very large distance. At short distance, you have a series of effects, and separating them, it's very, very complicated. So you can either resolve the ground state or next excited state, but not all the series. Okay, so this is what we do. Okay, we have a matrix element and the state, the energy of the state. And what we have now to define is what are these phis. These phis is what we refer to as interpolating field. And here it's where quantum mechanics comes at hand, because we use properties of the particles we want to measure to set property of this interpolating field, expecting then that the ground state of this interpolating field is our target particle. So for instance, before going here, let's give you an example. We want to measure a meson, a pion, and then what we put as an interpolating fields are a pair of quark-antiquark, right? With a specific flavor. So we want to measure a pion, it's up U bar or U bar D. And if you want to measure a kaon, it's an up and a strange, etc. So you put a specific flavor. You can put in, you need to select also, for instance, a spin and parity structure. So you do it via the gamma matrix here. And again, yes, I was a bit sloppy saying pion, but U bar, for instance, it's not just a pion. Pion is the pseudoscalar. Vector meson is the rho, the light one, etc. And you have various mesons. So depending on the gamma structure you choose, you are going to have a different particles. particles which are the ground state of the theory. But you know very well that a pion is not just quark, anti-quark, but there is all the vacuum effects into it. So, by creating an interpolating field that has the proper quantum number, you expect that as far as you separate far enough the particles, you will get a ground state that is the particle of interest, plus a lot of excited states. And so this is basically what you need usually to take into account in these when you construct interpolating fields. You need to take into account the flavor structure, the spin and parity, other symmetries, for instance, if it's even or odd under the exchange of up and down, etc. We give an example of this. Then you want to do momentum projection. So if you want it as zero, you can then use a Fourier transform to project it to a specific momentum. And you can get it as zero momentum or at any finite momentum. Still discretized on the lattice. It's not any momentum, but it's yeah, the momentum you can have on a lattice. And as well, usually you need to take into account gauge invariance and other symmetries. Okay. This is why, for instance, these two pair of quark antiquarks are put in the same place, because you know that the theory you are simulating its translation invariance, etc., etc. A simple thing you can do is to put them in the same place. But nothing forbids you to do some very fancy stuff. I don't know, put a quark here connected by gluon links that go like this. This pair here of quark antiquark is still something that will give you a pion at the end of the day. Okay, so it's this is just an interpolating field that, as far as you let it propagate it, you correlate to something else that has the same quantum numbers. Let's say we construct this, and at distance t we put the two quark antiquark in one point. You still know that these two objects have the quantum number of a pion, and so what you will find here in the middle when it propagates enough is a pion. Okay. This was the example of a pion. This is the example of a baryon. Let's say in a baryon you have 3 quarks, okay? And if you want a proton, it's going to be up, up, down. You want other things that are more strange, like a delta, it's u, okay? You choose again here. You want spin 1/2 proton, you choose the proper, spin 1/2 baryon, you choose the proper gamma structure. You want spin 3/2, you choose other gamma structures. But again, these are interpolating fields that give you the target particle that you want to study. Any questions so far? Yes. Sorry? Now we are rotated in Euclidean. So in okay, depends everything on the basis you take, but all of it here it's Euclidean, right? So yeah, it's a gamma 0. It's high gamma 0. Yeah. Okay. Any else? Okay. And for instance, you see here these quarks have spin indexes that are contracted like this, but then you see this notation that is A, B, C. These are the color indexes of the quark. And what do we do with those? Since we are at the same location, to ensure the antisymmetry and the Pauli exclusion principle, they need all of them to have different color, and so we contract with an epsilon ABC. And this is a particle, this is an interpolating field that has all the properties that we like, quantum numbers, etc. Okay. Now, and here it's an example for all the baryons, how you construct them, for instance, okay? And for instance, if you want a lambda, you can even distinguish between a lambda and a sigma 0. That this is interesting because although they have exactly the same quark content, UDS, and you know that the lambda has an energy that is slightly smaller, as a mass that is slightly smaller than the one of the sigma, okay? You know that these two are two baryons that undergo to missing. They are really small difference in mass. These are 100, slightly 100,000 MeV, and these 1,200 MeV, slightly. Some digits more. But regardless, these are two states. If you just construct a naive UDS baryon, what are you going to see? You are going to see the lambda, right? Because that's the quantum number you selected. spin 1/2. So if you construct a UDS baryon with spin 1/2, you're going to see the lambda. And the sigma is going to be extremely hard because it's going to be the next excited state. But what does distinguish the lambda and the sigma particle? They are distinguished between the fact that one is odd under the exchange of U and D, and the other is even under the exchange of UD. So you can see that if here you exchange U and D, on the lambda interpolating field, you get a minus sign while the other stays plus. If you implement this property, so if you don't just do a naive UDS, but you implement the fact of being even odd under exchange of U and D, you really see that the lambda interpolating field is going only to give you the lambda, plus other excited states that are the excited state of the lambda, and the other, the interpolating field of the sigma is going to be found. It's the next one. So you see as mass cap, okay? And this is how we do calculations, okay? Okay, so far so good. And let's do an example of how we are really measuring things, because now we talked about quark fermions, and these quark and fermions, we are not, we cannot directly simulate them on the lattice. It would be very nice if we can simulate fermions on the lattice, but that's an extremely challenging task. And yes, nobody does it. We want to integrate them out, like we had discussed. It's very difficult to target. So let's write down how it looks like the expectation value of the correlator of two interpolating fields. So these are two interpolating fields, like a pion in this case. So it's U bar D, okay? You put one at X, one at Y, and you let them propagate on the lattice. This is the expectation value of the correlator. How do you solve this? You solve it, you compute it by performing Wick contraction. I think you're all familiar with this topic. And the Wick contraction, what are they? Are just the only way reduces this correlation function to the only non-zero correlators. And how do you do it in practice? You do it by writing out all the explicit indices. Okay, for instance, for each of them we have color and spin indices. These are the indices of the gamma that are the were in between, right? This is task step one. Step two, we construct all the non-zero pairs. So you want to construct the pairs of QQ bar of the same quarks. So if you have multiple of them, you construct all the possible combinations. But here, U and D appear only once. And so you have D bar D, U bar U, okay? And a minus sign due to the exchange of quarks, et cetera, et cetera. These are your expectation value you want to compute. And basically, at the end of the day, what you want to measure is the quark propagator, because this guy now represents only one quark line, a quark propagator, propagating on the lattice. And these, what we have to measure at the end of the day, are these specific contraction of two quark propagators, one of the down and one of the up. One propagating from X to Y, one from Y to X, okay? So this is what we have to compute. Perfect. Are we done? We didn't remove quark propagators yet, so this is what we want to compute. Okay. Before moving to how we compute actual quark propagators, here it's an homework if you want to try it. It's a good pedagogical exercise to do it now, the same thing for the interpolating field of the nucleus. So you take n bar n interpolating field and you arrive down, and you should get this result. Where in here just a different notation, the D inverse is actually G. I will explain in a second what this means, but you should get something similar. Okay. So basically, a nucleon, you see in the nucleon where you have multiple U's, we have multiple terms because these are all the possible combination that you close the U. Right? You're familiar with this, right? Perfect. If you have questions, ask. So, the big question is now, how do we compute these quark propagators? These quark propagators, this is the other extremely challenging task of lattice calculations. On one side is the producing the ensembles that we discussed yesterday via Monte Carlo. But once we have the ensemble, we need still to measure quantities. And the measuring quark propagators is very, very challenging. It is challenging to simulate them, I'm going to tell you in a second, but as well as to measure them. So This is because what we do at the end of the day, we want to integrate out the fermionic field. So we have here the fermionic field, let's say the expectation value of a quark propagator is something you write like this. So it's the integral over the fermionic fields that are propagating from 2 points. And this is psi bar, this is your quark propagator here. And as well, at the exponent, you have the term of the action, this guy here, that is the Dirac action, okay? The Dirac term. Using properties of Gassman algebra, you can integrate this out. You had them in Dina's slides. You can show that the propagator is the inverse of the Dirac matrix. And the term you have at exponent, being a Gaussian, it's the determinant of the Dirac matrix. Then, okay, we don't have any more fermionic fields. Now, how do you define the Dirac matrix? You can define them in many ways. Dina showed you the Wilson action, etc. Wilson fermions, Wilson mass fermions. These are many different discretizations of the Dirac matrix. Okay, but it's something that is at the end of the day a matrix. It's just a matrix. It's nothing. It does not depend anymore on the fermionic fields, but only on you. All right. So this is a matrix. It's a matrix that describes how quark propagates. It's a very interesting matrix, okay? It's a huge matrix. It's a huge matrix because if you think about its size, it is a matrix that has the same dimension of a fermionic field. So we said it a bit yesterday. Okay, it's not on the whiteboard anymore. The gauge links are on the gauge degrees of freedom are on a link. The fermionic fields instead is defined on a site. But how many are the degrees of freedom of a fermionic field? Where are number of spin times number of column times the volume of the lattice. Okay? If you plug in these numbers, it's a really extremely large matrix. Let's do a second this exercise. If you do that, the one size of a matrix, let's say you have 4 times 3 times. How much is a volume? Let's take a not too big volume, but quite significant. For instance, 64 cube times 128 in time. Okay? But you don't see it there, sorry. Just a second, let me share all the screen. How do I share the whole screen? Why doesn't let me to share the whole screen? Anyway, let's share a second the calculator and then we go back there. So this is what you have. That's the volume. Okay, 64 to the 3, etc. This is the size of one lattice, which you can see it's already 402 million numbers. Ah, sorry, it's complex. It's complex, so I need to multiply by 2. Okay, so it's 800 million numbers on one direction. Okay, 800 million numbers. But this is not, it's one direction. A matrix, what is it? The square of it, right? So a matrix has the square of it, it's 6 to 10 to the 17 numbers. Okay, this matrix. A matrix, usually numbers on a computer, you store them in bytes, right? A double precision number in bytes are 8 bytes, okay? 5 to 10 to the 18. How much are 5 to 10 to the 18 bytes? Well, let's start dividing by 1024. This is kilobytes. So if we do it to the, you see you have 3 numbers. So this is going to be to the 6, are going to be 4.5, 1024 to the 6 numbers. So 4.5. What is 10 to the 6? 10 to the 6 is kilobyte, megabyte, gigabytes. So this is to the 1, to the 2, to the 3. Then you have terabytes to the 4. Then you have petabytes to the 5, and then you have exabytes to the 6. So if you think about it, this is 1 million terabytes. It's something ginormous. You don't want to store this thing. You cannot store this thing. Okay. Let's go back there. And this is for a small lattice. For a much bigger lattice, it's much worse. So how are we then going to compute the inverse and this matrix? Well, something comes to our advantage because the matrix itself, the direct matrix, is actually a sparse matrix. You have many, many zeros all around. A sparse matrix is a matrix that is not dense, but it's mainly zeros. So the real number you need to store when you want to compute the matrix D are proportional to the volume. So it's not proportional to the size, not to the size square. So it's something, this is about 12 times the size of the matrix. It's not too big, it's not terrible. It's a square root of this, okay? So it's something that is manageable. It's order of terabytes, okay? But we want to compute the inverse. Unfortunately, the inverse of a sparse matrix is not anymore sparse. It's going to be dense. So the complete inverse, okay, it's impossible to compute. Much worse is the determinant of D. The determinant of D is a computed determinant. It's always a problem, even though it's sparse, it's always a problem that goes to the V to the cube. So it's even worse than what we said. Computed determinant, it's not a V square problem. Computed the inverse, it's a V square problem. Computed determinant, it's a V to the cube problem. Terrible. So you need strategies. You need some applied mathematics and other numerical methods. And what comes to our advantage is the employment of Krylov methods to solve the linear system dx equal b. How many of you know about Krylov methods? How many of you that does applied mathematics? No? Okay, I think this is interesting for you. So solving a linear system dx equal b, it's actually much, much more easy because your goal at the end of the day, if you solve a system dx equal b, what do you find? If you solve it, you find x, what is x? It's the inverse of d computed on b. Of course, this is what we want. But this is much easier because what you are computing is not the full inverse, but a vector that has information about the inverse, okay? But not the full inverse. So this is the main task where we really put a lot of effort on our calculations. This is where all the cost goes here to compute these linear systems. We solve linear systems all the time because we want to compute how a quark propagates. You see, this is a quark propagating. So for instance, you want to find out, like we had here, a quark propagating from a point x to a point y. A quark propagating from point x to any point y, it's basically a column of the inverse. And so if you put your b to be a unity vector, the x then, that is the d inverse equal b, represents this unity vector that is centered in x, represents x, represents all the propagation of the quark from a point x to any point y, because it's a column of the inverse. Right? So if you put a unity vector, we place it in a position, and then we can propagate it to any point. If you want to compute, for instance, a trace of the inverse of the Dirac or the determinant, there are again, stochastical methods that boil down to computing, to solving linear systems. For instance, the determinant, you can, well, maybe here I go too much in detail, but for your information, the determinant can be written down as the determinant of D can be written down as the exponential of phi dagger D inverse phi. It's something very similar to, okay, it's something very similar to what you have here. The reason why with fermions you get the determinant of D is because you are integrating over the fermions, you get the determinant of D. On the other hand, if you do not use fermions, but you use bosons, the fermion, let's say, standard fields, the determinant of D is represented by Gaussianly distributed variables, where you can compute the inverse. If you sum statistically over many of these phi's that are Gaussian distributed, you get the determinant of D. So for instance, again, everything boils down to compute an inverse. So you compute X, which is equal to D inverse phi, where phi is Gaussian distributed, and this guy, e to the minus X, it's your determinant, stochastically. You compute it many times, you get your determinant. Okay? These are all numerical methods. Okay? And we are going to do this. Perfect. Okay, so did we solve all our problems? No, unfortunately no. Why we didn't solve all our problems? Because there is another critical, very extremely important factor of this Dirac matrix, the mass. So when can we compute the inverse of a matrix? As far as the matrix is non-singular. The very big problem is that when in the limit of the mass that goes to 0, our Dirac matrix becomes singular. A singular matrix cannot be inverted. Fine. A non-singular matrix can be inverted. Perfect. But the fact that the matrix is, by the way, I'm not in full screen anyway, but the effect of this matrix becoming singular can be seen in a time to solution that grows exponentially. So basically, it's diverging, and as we decrease the quark mass of our system, it costs more and more and more and more to invert the matrix, because it takes a lot of iterations. So these are iterative solvers, and you stop once you are very close to the solution. There are many iterative methods here. And basically, what you see is that if you decrease the mass, you need to keep iterating to find the solution, and you need to iterate forever as you go smaller. And so you see that the time to compute, for instance, a quark with a strange quark mass takes 10 takes here, and the other takes 10 times more, and you go further. And this was the reason why, for many, many years, people simulated a larger than physical pion mass, and they preferred to take a limit to the physical pion mass because it was extremely costly. Again, you develop numerical methods. There is a nice solution to this. That is multigrid methods. I don't think I will not delve deeper into that, but multigrid methods are nice methods that allow you to accelerate significantly, and so by changing the algorithm, you can speed it up a factor of 100, and then you simulate here very efficiently. Okay? So, but this is why lattice simulations are difficult. You need systems are huge, you need very advanced numerical methods to speed up calculation, because what you want to compute are challenging numerical quantities, and you need to compute propagators all the time. Okay? So for the sake of time, I will skip these. It's how we compute traces that are disconnected quark loops, or how we compute pion two-point functions, but I explained it a bit now, so it's I think it's fine, unless you have any question. And in the same way, to compute nucleon two-point function is we use point sources. So we select one point of the lattice, and then we compute, like I said here, these propagators to any point, and we contract them. So you just take them and then contract them properly after a certain distance, and you get, for instance, nucleon two-point functions. Let me see what. Okay, let's go here. Okay, are we fine? Okay, I drink a second water and. So, finally, we have a correlation function, okay? We do all these calculations, and what we get after inverting, contracting solutions in the proper way, you get correlation functions. And you have a correlation function like this. I'm going to give you one now in a second. And these correlation functions, like we saw yesterday, being a correlation function, decrease exponentially. You have this beautiful, in a log scale, in a semi-log scale, you have this beautiful linear decrease, but this is an exponential decay. And you know you want to identify a ground state where you can select the mass. So if you are able to identify the region where you are dominated by one single state, so after a very large distance you have only one single state, then this single state is your mass of the particle you're interested in. Okay? A very effective way to, we will see it in a second why, to extract this state is by building up an effective mass that is the ratio of two correlators, and you see very easily that if you divide t by, if you divide exponential, you take the logarithm, you get the mass only because the overlaps cancel with the ground state. If you assume ground state dominance, the overlap cancel, and you get that. This is very easy to prove. Fine. So we use this strategy. We plot them out, and what we see are something like this. So here it's case of a nuclear interpreting field. We have a scale here. Again, this scale means nothing. Okay, this is actually already in physical units, so maybe, yes, it's in. So this is 0.94, and no, I'm not sure if it's anyway. The scale here at the moment means nothing because you know, you need always to define a lattice spacing, etc., to define a scale. So these are correlation. These are results, but then you need always to put it on a scale. And these, okay, I will not go deeper into that, but you edit in Dina's slide. So you can use other masses to define a scale, and then you compute mass gaps. Anyway, we do the effective mass, and we have these two results. This is the pion. The pion is beautiful in terms of error, but something is happening here. Okay? And the nucleon instead has error increasing when we do this effective mass. But here, kind of, you see some plateau happening. Here, you see some plateau. You expect this plateau because you expect to extract the mass. And yeah, at the moment, yes, in both it's a bit difficult. Why? There are these two questions. Why this one is not plateauing? Do you have any idea why here we do not see a plateau for the pion, although we expect ground state dominance? Why? What was happening yesterday? Why the correlator was going up again and not just going down? It had periodicity. So the pion that propagates beautifully along the lattice, it fills itself over and over, and we are going to fix it in a second. The nucleon instead decays much faster, okay? But it has errors increasing. Let's try to reply to these two questions. So first of all, the pion. The pion, of course, it loops over and over. So on one side, the correlator that propagates forward decays exponentially like this, like we said it. A propagator that propagates backwards decays exponentially like this, okay? So the propagator forward decays. When we measure correlation function from a point that starts at 0, we propagate towards t. We decay, we propagate towards minus t. We decay another way. But then we have the lattice is periodic, so we go up again and down because it's periodicity on time. Perfect. So this is the one propagating forward in one way, propagating backward in the other way. You understand if the mass is large enough, this you will decay for a long time before, you will decay very fast, sorry. You will decay very fast and before filling it itself. If the mass is small, instead you fill yourself many times. And if we put these in a formula, basically, at leading order, you have the one forward, the one backward, but if you consider it propagating an infinite amount of time, you have a geometric series here, and this is the final result. Very often, this is enough if your time extent is very large. You don't fill yourself multiple times, only once. But if your time extent is very small because you do finite temperature, so you do have a very small time extent, then you need to use a formula like this. But again, it's fine. We can fix it. We know how to fix it. We still assume ground state dominance, and you propagate multiple times. So we fix this, and for the pion, then finally we get something beautiful. We get this one, okay? This is really beautiful, and actually it's extremely beautiful. The error do not increase, it propagates everywhere, and you say, ah, okay, I take a beautiful plateau here, and this is my pion mass. I really see the pion ground state. For the nucleon, it's a bit more difficult. The errors are increasing exponentially. Why are the errors, what do you expect? The errors to increase or not to increase? Which one is the anomalous one? Something exceptional is the pion that does not have increasing error, because if you try to measure correlation function at large distance, it's very difficult. It's a very difficult task. And this is actually the norm. The norm is that the error increases exponentially with the time. But there is a very nice answer to this, physical answer, okay, that I'm going to show you now, because this is very important, and this is to estimate also how the errors increase, okay. This is something that is known as Parisi-Lapage argument, and it's the following. A correlation function is something that it's the correlation between two interpolating fields. The variance of a correlation function is the square of it, right? So it's the x square minus the mean square, okay? This one. So a relative error, if we do sigma divided by c, you get this formula here. This is trivial, right? You do the square root of it, and you have this result. All good up to here? Okay. So let's have a look a second to these two quantities. What is it? What is this field? This is the standard interpolating field. Okay, this is the interpolating field that starts from 0 and goes up to t. While the other, it's the square of it. So you are going from 0. You start from 0, you go to t. Okay, but the other has also the opposite as the bar of it. So if you're doing a pion, you compute this, but then from t you go back to 0 in the other one, in the squared. Okay, because you have it squared in this one. What state we expect to be dominant? So the ground state that we expect to be dominant here might be different than the ground state we expect to be dominant here. So here we said that our ground state is a pion. Here might not be a pion square, might be something else. So if we assume ground state dominance in both, you can easily find out this formula where you find that at the numerator you have the mass, the energy of the state square. You see here, this is like a quark, a 4 quarks interpolating field when you do the square. So you have the ground state of the interpolating field square. You have it twice, divided by twice the energy of the ground state of the interpolating field not square. Okay, this is also some trivial math when you just plug in ground state dominance. You expand, you go a leading order, and so at a large t, you expect the relative error to be proportional to the exponent of the energy difference between these two. Okay? All good up to here? So you put it here, at large t, this is going to dominate, and etc. Okay? Now let's see what happens. In the case of a pion, the state square, this energy here, are just 2 pions because there is nothing smaller than a pion. Even if you put 4 quarks, 2 pairs here of u bar, let's say u d bar, d u bar, and you combine these 4 quarks somewhere else, the ground state of it is just 2 pions propagating because there is nothing that has a smaller energy than a pion. Okay, so the pion being our smallest, the state with the smallest energy, even if you put 10 pairs of quarks, that's going to be 10 pion masses. And thus, the pion has an error that does not increase exponentially because the energy of the state squared, or the interpolating field square, are 2 pions. The 2 simplifies. You have mass of the pion minus mass of the pion 0. And this is beautiful because you know that now your interpolating field is a constant error. You really see it, this one. Okay. For the nucleon, it's much difficult. It's much more difficult because if you put a nucleon and an antinucleon pair here, you have u D and U bar, D bar, and all of these, they combine to each other, not as 2 pairs of nucleons, no? Because this is, when you put all these quarks in one place, they don't give you 2 pairs of nucleons, but they give you 3 pions, because you pair them up as 3 pions. Okay, so if you put in one point UD and U bar, D bar, and these are all 6 quarks in one point, you have other 6 quarks of the same, you see that these are pions propagating, are not nucleons. And therefore, you expect the error of the relative error of the nucleon to grow as the difference of the nucleon mass minus 3.5 pion masses. And this is quite a big exponential, so this is how your error increases. And you all see this stuff on the lattice. So all these correlation functions you measure, you really all see for all of them all these physical properties. So this is very, very interesting, because you see in practice all the effects you expect by quantum mechanics, okay? So you see really the effect of quantum numbers, etc., etc., etc. So it is a very nice, interesting way to study eigenvalues problem, because what we are studying at the end of the day are eigenvalues problems, but done within the framework of quantum mechanics. And it is very interesting. Okay, any question? So by using all these arguments, you can see how fast you expect your error to grow, depending on the particle, etc. You know the masses, etc., etc. Okay, how are we doing? 52, okay, yes. Let's keep a bit this. I mean, Dina told you a bit about this, so there are ways to improve the signal to noise ratio. These are all methods we develop. And for instance, something that is very interesting is the usage of low mode averaging, where you compute exactly the infrared part of your operator. Actually, this is quite interesting, because what we said is that we cannot compute exactly the inverse of the Dirac matrix, right? Because it's too expensive, it's too big. But something you can compute exactly, instead of computing the whole index in Dirac matrix, is to compute a subspace of it, right? So you know that your matrix, a matrix, you can always write it as a sum over eigenvalues and eigenvectors, right? Okay, depends if this is Hermitian. Let's consider for simplicity an Hermitian matrix, etc. You write it like that, right? And an inverse of the matrix is just the inverse of the eigenvectors, right? Trivial stuff. So the inverse of the matrix, what is dominated by? It's dominated by the low modes. Because at large distance, what is propagating on the lattice are not the ultraviolet modes. The ultraviolet modes decay very fast when you have these are the equivalent of the large masses. At a large distance are the low modes of it. So if you're able to compute exactly the infrared part of it and write it like this, plus the rest, if you're able to compute this exactly, you can reduce significantly your error. And this is, for instance, another technique that we use where we compute exactly the infrared part of it, and we can get, for instance, these propagators. And this is beautiful. Look at it. It's a reduction of the error of factor of 5. The variance is a reduction of 15 in the variance. So you can see that we can compute correlators that propagate much, much farther. And these are all techniques that go behind these calculations. Okay, because at the end of the day, we want to compute precisely correlators. Okay, let's move. I will move now to the notebook. I will do like yesterday. I will combine this with a break, with a short break. But like I said, then I need to resharpen. So yes, let's get back. Let's not spend too much time on this. Okay. Again, you can go back to the notebook we had yesterday. I added a part 2. And here it's a bit about this, something more that might be of interest of you. So now we will do some tutorial on data analysis. And okay, what I'm going to give you basically are raw correlation functions of the nucleon. So you're going to have data like this, that you can download them by using this command here. So you can get them from my Google Drive like this. Okay, the notebook. You load them with NumPy. It's a NumPy array. And if you just plot, what you get here are, for instance, 400 results measured on 400 configurations, okay, for a time separation of 80. So this is the data. These are 400 samples. All the data points are these 400 samples of a correlator that propagates from 0 up to 80. Okay? And this is the data we have. Let's have a look a bit to it. So this is the data that comes out from a simulation. And the first thing we want to do from this data is to start to doing some statistical analysis. The technique that we use for doing statistical analysis here, it's known as jackknife resampling. How many of you know about jackknife resampling? You use them? No? Yeah. Okay. So jackknife resampling is a very useful analysis technique to automatically propagate errors. Okay? Because this is a very challenging task. You have this data, but then you don't want just to compute the correlator. You want to compute derived quantities like the effective mass. So computing the error on the correlator is simple. If you assume that these are the correlators, we can do like we did yesterday. You compute the variance of the standard error and you get it on a correlator. But then you want to compute a derived quantity like an effective mass that was defined like this. And yeah, how do you propagate the error? You don't want to do it manually, right? You want to do some automatic way to propagate the error. And the automatic way to propagate the error is that we use is jackknife resampling. You can also use Bootstrap. I don't know if you're familiar with Bootstrap, but jackknife is equal. And the idea is the following. Instead of having a sample of a correlator, what we want to create now are samples of the mean. So we don't want to sample the correlator, but we want to sample the average of the correlator. Okay? Sampling the average of correlator as an effective way of doing it is by summing overall possible data apart 1. So if you do the mean overall possible data part 1, you get something that is extremely close, like it's written there, the sum overall data part 1, you get something that is extremely close to the real mean, the mean of all your data, apart for a small deviation. It's trivial, right? You're summing overall apart 1, but this is interesting because the small deviation that you have, so this x bar I is something that approximates x bar plus a delta of x bar, a small variance at there. Yes, a small variance here, okay? And this small variance now we can use it to automatically propagate error, because now if we compute functions of this x bar I, okay, you can understand that you can easily the result of this should be equal to the function computed on x bar plus something that is proportional to the derivative of the function with respect to x. If there are many variables, let's say you can have also multiple variables, times the delta x bar I. Okay? And you already see that this, by doing proper statistical analysis, this is equal to a variance of the function. Okay? It's to an error. So this is interesting because now, if you compute a resample of the mean and you compute derived quantities on it, then your mean of the function, this you can prove it analytically, a part of some small corrections, it's equal just the mean of all these. So you can show that if you sum over all these 1 over n, you get this term. But the standard error on that function, you can get it by that other formula. Okay? By computing the standard deviation of the function without this piece, this is the standard deviation of the function times n minus 1. Okay? Any question? No, perfect. So let's see it in practice, this effect of jackknife. These are the 3 functions I give you here. So you do the jackknife resampling a trick to do it is by summing over all possible value, and then you want to subtract one of them. So doing the sum over all apart one, you can sum over all and then subtract the I. And if you divide by -1, this is the mean over all of them. So this is an effective way of implementing it. And then the Jack mean, the mean of that is the mean of the results over all the array, and the Jack error is defined like this, the standard deviation times the square root, okay? So if we apply jackknife, the array, we apply the jackknife, we go from what we had before to this, that you can see that for every sample, the jackknife resampling, it's barely noticeable here, the deviation, but here you have all the 400 samples, they're all falling the same point because all the 400 samples are just mean apart a small deviation. And this deviation becomes bigger where the error becomes larger, of course, right? Because when you do the mean here, you have a much larger deviation, right? And then we can use jackknife mean and jackknife error to compute, to put an error on this correlator, and you see that the error is tiny up to here, and then it starts to be significant. These red points are part where the correlator became negative, so it's just to show you, because if I don't put negative correlator, then yes, it looks weird. You have empty points. But this, because it's a log scale, and this empty area is just where the correlator became negative. So I just flip it up to show you. But you understand that this, of course, it's a function that decays exponentially. It's not positive definite, and so here it fluctuates around 0. It can be positive or negative, but within errors. Here the errors are small. Does this mean that there the function is negative? No, a correlation function is always positive definite, the final result. But it's a statistical fluctuation. So the problem here is that those errors are not properly estimated, okay? You know, there is always an error on the error, etc. So if you have too few statistics, although these errors are small, we cannot trust them. Actually, you cannot trust your error much, much earlier, okay? How do we see this? Let's put the physics I discussed a bit before at use, and let's plot now two things. Let's plot here how the error goes and the mean. You can see that actually the error, it's beautiful, yeah? The error decays like this, and this decay is what we discussed before. It's a difference of the nuclear mass minus 3.5 pion, okay? It's a different exponential decay. While the mean decays like this, so this is the decay of the nucleon. And you see that our statistic, if we push our statistic further, we make this error smaller and smaller, and so we gain significancy, but there is this somewhere here, this crossing point where the error is larger than the correlator, and so everything goes wrong. So how far have we been able now to measure properly the correlator? Well, we've been able to measure properly the correlator. Let's see up to where. Let's plot now the relative error. Sorry, let's plot it first over all 80, just to show you the effect. So if we plot it over all 80 data points, you see this error growing exponentially and then doing some random stuff there. All these errors that you have here are really non-reliable. It's not that the error grows but then becomes smaller, etc. It's just the wrong error, okay? And up to where can you trust the error? Where you can trust the error usually up to a point where your signal is 1/5 of the error. So where the relative error goes up to 0.2. And you can see here that if you fit it, this exponential decay up to a given scale is exactly that mass of the nucleon minus 3/2 mass of the pion. Then up to here you have your physics. Over here it's numerical instability. Okay? So our data are good up to here. We need to cut it. If we cut our data there, which is 39 sourcing separations, we define this Tmax, we plot it again, we get the correlator we want to fit. This is really the correlator we want to fit. This is where we can trust both the error and all the statistical information. Okay? So this is important. So the data you want to analyze is the one in this range 1 to Tmax. I forgot to, okay, someone should have asked, what is happening here? What is happening at 0? At 0, it's what we name a contact term, contact point, and if you write it down, what you are doing at 0, you're not measuring correlation function because you put everything in one point, right? So you're measuring completely something else. That's the inverse. That's you're measuring the trace of the inverse of the Dirac operator but contracted in a specific. You don't want to care about that. Your correlation function starts when you separate them. Okay. So when you contract everything in the same point, is something that has a completely different meaning. But your correlation function starts after. You have excited states, and then you have a plateau. Okay, you have a convergence. Good, good. So our final data we want to show it's from 1 on, up to Tmax. That is where reliable. Fine? Perfect. Here are a few exercises for you. You want to construct the effective mass and plot it. You want to make a plateau fit of the resulting effective mass, which is, you should get a plot like this one here. After you do the effective mass, you should get, yes, a plot like this one here, right? And you want to fit it to a constant to get the energy. And then something else that it's quite nice if you have time, but anyway, you're not going to have, is to do the correlation matrix. But I will give you the solution because also that's quite interesting. The correlation matrix of T and the effective mass. Now let's do a very break/exercise pause. Let's reconvene at 20. Are you okay? And then, yes, I will give you the solution and I tell you a bit more of things. Okay? Yeah, you can, let's see what, hopefully, if you got something and what are the solutions. I mean, I must say it takes more time than this, but okay. It's something, if you like, would be good to try again. Though, let's go over these solutions, basically. I mean, it's simple if you know what to do, but of course, it's not that easy. Like, you want to build up the effective mass. We said this is the formula. We are using jackknife resample data. The formula is extremely simple to implement using NumPy, and it's basically just the ratio of the array up to the last data point in time, the second to last data point in time, divided by the array shifted of 1, okay, in time. So this gives me the ratio of T divided by T plus 1, okay? Why am I putting the indices here and not T? You need to be careful, you need to put the indices here. This is because we want to stay within the jackknife resample data. And so your data that had a shape 401 data point and 38, I remind you that 400 data points are the various samples of the mean over different configuration, here in the case over the averages. While the 38 data points are the time separation. So the ratio in time, you want to do it in parallel, you want to broadcast it over all the 400 for different times. You don't want to mix the 400, so you divide for each of these 400 one by one in this way. Then you take the NP log, and the log is going to give you samples of the effective mass. I mean, if we plot them again, let me try to do this. If we just run the effective mass and we simply naively say plt.plot f mass, sorry, I need to transpose it. Otherwise, yes, I'm plotting in the other way. Yeah. Let's put, these are lines down at points, but again, it's all of them, they look the same apart of small deviations because we did them over these jackknife samples. Jackknife is a really critical and extremely useful yeah, we don't want all of these. Let me remove this cell. Jackknife is a really critical tool, because what we do here, it's quite a complicated function. It's a nonlinear function. Jackknife doesn't care. It propagates properly the error through everything. So as far as you keep doing things on Jackknife samples, and then only at the end, once you're interested in getting a mean and an error, you get the mean and the error, this is the result. So you need the critical point of Jackknife resampling routine is to just to resample the data, just then do on them whatever you want. Okay, you keep doing, you combine them between different data sets, etc., etc., etc. And then once you arrive to your final quantity, you take mean and error and you show it. Okay, and that you expect to be the correct error, as far as the data are reliable. Of course, in the region where as we saw, the data are not reliable anymore, everything is not reliable. Okay, this is the effective mass plot. Fine. The next task was to fit these two constant. Fitting these two constant, you can either use do an average over the points, a weighted average, you want to weight with the error, or you just use a fitting routine, like, I don't know, SciPy optimized curve fit, this is fitting data. But again, okay, in one way you may want to get the covariance. I don't know how many of you are familiar with fitting, but usually if you want to get an error on the fit result, okay, you need to pass the errors, and then this fitting routines gives you the optimized parameter plus the covariance matrix of the optimized parameters, right? So if you have many of them, these are the optimized matrix. These optimized matrix of the covariance parameters carry the proper error as far as you are giving the covariance matrix of the data there. Otherwise, if you do an uncorrelated fit like here, that error is maybe underestimated, etc. Okay. Regardless of this, we do not want in this case to use the covariance matrix of the fit parameters. That is an information on the error. But we can just simply use Jackknife over and over. So instead of doing a fit over the data and compute the covariance matrix, we just fit to constant the data for every Jackknife sample. So for every line of this set of data, we fit them to constant. And we get here n samples of our final result on which again is information about the error, and then we can take the error on it. Okay? So this is how powerful this Jackknife routine is. It's just to keep doing things on each Jackknife sample, the same code, and only at the end you care about taking errors. And this is going to have the same error of the other as far as you did things properly. Otherwise, this is more correct because it takes into account the correlation. So this fitting routine is an error, and then we fit it for every mean. By mean, I mean every line in this array, okay? For every set of data. And this is just a fit to constant. So we have one parameter, we fit it to constant. It's easy. So I don't need the X dependence, okay? That is the time, but yeah, it's not needed. If you want, you can try to do a multi-state fit, etc., but this is more advanced. So this is a function that fits to constant and returns the samples. Okay, now what we can do, what was part of the exercise, was to fit to constant the mass starting from different points of this, because as you see here, we expect ground state dominance only a large time. So you want to fit this region, this region, this region, up to get the result and combine all the data. And how I'm doing here, this is by fitting to constant the effective mass over all the samples starting from T on. And you plot it, and this is your result. Perfect. Now we are able to combine the data that we have read information, cut these fluctuations, we get these beautiful results, and now we're able to say, here I see convergence, I pick this point on, this is my mass. Okay? There is a bit more to it to get the correct error, etc., because you want to account that, but this is, for instance, okay, a final result. Okay. Something also very interesting of this, it's that you could have tried to fit the exponential this one. This you should consider it an exercise. If you try to fit exponential by this one, you get very different result than the fit of the effective mass. unless you do a correlated fit. How many of you are familiar with correlated and correlated fit? No? You know, the definition of your chi-square, your fit, many of you are familiar, okay, you are familiar with the chi-square, but the chi-square you put there, the proper definition way to propagate error properly, propagate error properly and minimize it, is to introduce between the samples, so you have y minus f of x I, is to introduce transpose here the inverse of the covariance matrix. Here you have yi. These are vectors, so it's not I. These are vectors, and it's these plus minus f of x vector. So many of you, in most cases, okay, might have used only the a definition of the chi-square where instead of having the inverse of the covariance matrix, you have only the diagonal part, which is the error. And so basically, these are d squared. These, if you only consider the diagonal part, you get d squared divided by sigma square, which is the diagonal of the covariance matrix. You know, in the diagonal of the covariance matrix, you have only sigma square everywhere. And then here you have the covariance x and y. Etc. So if you consider only the diagonal, the error only, you obtain this. This is what, for instance, curve fit here does by providing only the error. But if to curve fit will provide the covariance matrix, then the error you get here, it is the correct one. Okay. Independently on this, what is interesting is that if you try to fit the exponential, you get different results with smaller errors, but that's not the proper error. And you will get the proper error only if you introduce the covariance matrix. This is because the data, or the correlator data, are highly, highly correlated. You can see here that the correlation function, you have a certain time t, is highly correlated up to a distance. So if you start at 0, you are correlated up to 20 times separations. Okay, this is not a covariance matrix that is diagonal. Something very interesting that happens, and this is why you can, well, if you plot, well, you don't see it really, but if you plot only one correlator, you see that are nice, they are waving, they're not jumping all around. They are very nice correlation function, waving out, etc. But this is because of this correlation. If you do the ratio like in the effective mass, this is another critical point of the effective mass like this. Something extremely interesting is that you fully cancel the correlation. And these points here that are jumping like this is because they're not correlated at all between each other. And this can be seen here, that if I do the correlation matrix of the effective mass, you have one only the diagonal, and then everything here, although it's colorful, it's a random fluctuation around 0. So by doing these ratios of correlation functions, you're actually constructing something that is has lost completely the correlation. Okay, yes, correlation in time. Okay, so fitting to constant the effective mass, like we are doing here, is much more safe than fitting the exponential to the correlator. So the other requires more, a better ball. I mean, it requires computing the covariance matrix and the inverse, and yeah, more advanced techniques. Any question? No. Okay, so here you have some code, and you can try a few things more if you want to fit the other, to add excited state contamination. That is what we do often. So you know, just a second, let me jump. I think I have here. Do I have it? Well, you know, anyway, you know you can expand the correlator as a series of exponentials. So instead of just fitting to constant like here, you can try to fit earlier. Here there is a pink band, or much earlier. So these are 2 states, or much earlier 3 states, and you try to put multiple exponentials and try to describe and get the masses of the larger states. You can try to do that, and you will see that you have very large errors on that. I will come, well, let me start from here and then jump back. So this is an example from our lattice data. This is the ground state of the nucleon, and the first excited state we measure is this one that is compatible with the Roper, but you see the difference in error. The ground state of the nucleon we measure extremely precisely. Here are, I don't know, 20 times the error, etc. This is why it's so difficult to do excited states analysis and to measure complex states. But I will go back there in a second. Let's start from here. We finished with exercises. Now I will tell you a bit more about hadron structure and how we compute them. And this is also very interesting. And it's the numerics of it. So I just need to remind the time because, okay. So, okay, mass spectroscopy, it's something we understood. We're measuring energies, okay? The exponential decay, it's the energy. But there is much more to it, and it's our ability of measuring matrix elements, of measuring expectation values directly of states. Why this is interesting? Well, take, for instance, as an example, the neutrino oscillation experiments. Something that they are very interested is to know more about the quasi-elastic regime at low energy in this region here, where experimental data is not much precise. So this is, for instance, a kind of case where the experiments look from input from lattice QCD. Okay, and how do we provide this input? Well, we want to study this kind of transition, basically a semi-leptonic decay, or depends a bit if you are in the space-like region or time-like region, but regardless, we're interested in this. So we're interested in having a proton and a neutron and an exchange of an interaction of it with a boson like W boson. Now you may tell me, but on the lattice you're simulating only QCD and not weak interaction, QED, etc. Fine. We don't need to do so though, because all these interactions, what we are interested to compute, it's this end of the diagram, okay? The case where a nucleon interacts at some point with a boson that has a certain quantum number, gamma mu, in this case. And then we don't care about this other end, this other vertex of it, that you can compute it with perturbation theory, etc. You can resolve it, integrate it out. We are only really interested about this. And this is what we refer to these matrix elements. So we are interested in matrix elements where we have a current that it's either, for instance, a vector or axial current that it's interacting with one of these valence quarks of the nucleon propagating on a lattice. Okay? Now these are physical states, are not interpolating fields. These we want meant to be nucleon and proton. Okay? How are we going to compute these? Let me skip these. Okay, you can compute different kind of currents. You saw this with Dina. How are we going to compute these? Well, again, we need to go from the case where we have a current put within interpolating fields, yeah, to a matrix element. So a matrix element where we have the really ground state nucleon and the current in the middle. What are the steps of doing this? Well, we measure again correlation function. Now a 3-point correlation function. We don't have 0 and TS, but we have only also teams, subplace where these current couples. And if you do these contractions here, it's not about the contraction, it's about the physical result. You see that if you let them propagate far enough, and you insert a complete set of states in the between here and here, okay? This complete set of states is again a series of exponential where we a ground state the dominance with only one state surviving, which is our ground state particle that in this case is the nucleon, right? Then you have all the other states, but we assume in ground state dominance, all of them are exponentially suppressed, and you have only one surviving. So by introducing the ground state only here and here, you see that on one side you have the overlap between your interpolating field and the nucleon, the exponential with the energy. Then we have the matrix element of interest, the nucleon, the nucleon interacting with the current and the nucleon, and then we have the other end of it. Okay? If you put in these, computing this on the lattice is very simple. I don't have it here, but computing this on the lattice is again about just doing contractions. You can see it here. We are just contracting this fermion propagator somewhere in the middle, etc. Dina said a bit about this. And you have that. But how do we extract this ground state then? Well, it's again simple. We need to go far enough. We need to separate them very far. If you separate them very far in the middle, you have the nucleon. You have these. We're interested in isolating this term. And we can isolate this term by simply removing these two. How do we remove these two? These two, we get them from a two-point function. Because if you do the same expansion for a two-point function, the two-point function, we saw it before, has a coefficient C0 in front times the exponential. Before, we didn't care much about what C0 was, right? We had, well, I need to go too much back, but you know, we have an overlap, and well, like here, we have the amplitude here times the exponential. So far we cared about exponential, but now if we look at what is the amplitude of the ground state is, by inserting the set of states, is the overlap of the interpolating field with the ground state. This guy alone doesn't have much meaning. It's just a number that is how well our interpolating field is interpolating with the ground state. But it's extremely useful because it allows us, when we take a ratio of three-point function and two-point function, to cancel exactly these overlaps here and remain only with the ground state matrix element. So by taking a ratio of two-point function, three-point function, you will see that these overlaps cancel, and you're left with this guy. Then the energies, there is some more stuff here because you have the things, dependence, etc. If you want to completely cancel the energies, you do this square root, and this cancel all the exponentials. But basically, this ratio here looks complicated, but it's the same thing you did now with the two-point function. It's a ratio of three-point function, two-point function. If you compute this ratio here at large sourcing separation, you get this. And this is everything we want, okay? Good. Now, how to compute three-point function? We're not going to that because otherwise it takes too much. Well, if you have time. But for instance, from our calculation, if you use the proper method, it's extremely interesting because cheaply you can put inside here any current, and then by being able to put, okay, let me say a few words, here in the middle any possible operator, you get in one go a lot of physics because you get axial form factor, magnetic form factor, transfer form factor, everything depending on the current you are putting in the middle. You can put the derivative operator, and then you get really a lot of physics about these form factors. Okay, and this is what we provide you. But how do we extract them? Again, to arrive to these results, we require a very careful analysis because, like we've seen here, it's very complicated to assume ground state dominance, but we could fit it to constant. Doing it for matrix elements, it's much, much more difficult because it's very difficult, it's very expensive due to the costs to arrive to a region where you really see a ground state. You never see a plateau. You expect this formula to give you the matrix element at large separation, but you are never able to arrive to large enough separation to really see a nice plateau, okay? So this requires more analysis. You know, the physics tells you, though, that all of these, you can fit it as far as you assume higher states. And this is what we perform. So for instance, if instead of having only the ground state, we add the next excited state, you are fitting this data by having the ground state matrix element, but also the overlap with excited states that they're there, and you can fit all the data nicely, and then you can extrapolate to large time. Okay? And this is the way we extract the ground state matrix elements. Okay. This is just to give you an idea. You see here that for each of these points to have a constant error, what we had to do is to increase the statistics, and we had to increase the statistics exponentially. So to measure these sourcing separation, for each of them, we had to do a dedicated run. And so to measure the 3-point function separation rate, we used over 400 configuration, one source position, at 10, 2, and as you go further, the error increases exponentially in this TS, and so our statistics to increase exponentially too. Okay, and this becomes very, very expensive, very, very fast. This is why it's impossible for us to go that far with errors. Of course, you can let the error grow, and then it's useless because you have huge errors, and yeah, again, it's as useless as this data here. Can you get a plateau here? No, you cannot. You need to do a multiple state analysis. You do this, you do many fits. We use more advanced techniques because you don't want to be biased. So you do techniques like the model average, where you do many fits, you weight them with a chi-square, etc. These are very interesting. This is a reference if you want to see that. But you see, we fit this data in multiple ranges with different intervals, etc., etc., etc. And these are all the fits results. Then you don't want to pick up only one, you want to consider these fluctuations between them, and so we do model average, and this is our final result that we can claim. This is the result done over 3 ensembles. You take the result over at least 3 ensembles, then you take the continuum limit, you extrapolate to a square equals 0, and this is really the physical quantity in the ISO-QCD limit. In the limit where we have up and down quarks that have the same mass, and non-QAD effects. If you then want to correct it beyond that, it's possible, but requires more calculation because you want to correct for all additional effects. But in the ISO-QCD limit, this is the final result. Okay, and the line is the experimental value, etc. Of course, here lattice QCD does much worse than experiment, but for all the rest, lattice QCD can give interesting predictions. And this was what I was referring to. While you can measure experimentally very well the charge, the form factor itself, actually, it's, do I have it? No, I don't have it, but it's competitive with experiments, and yeah, it provides input for it, okay? There are also disconnected contribution, of course. Disconnected contributions appear when you have quarks of the same flavor in the current, right? So if you want to do some more structure, not like here where if you want to do really structure and not decays, in decay you have the quark changing flavor. Let's take you do a lambda 2 nucleon, you have an S that becomes a U, and you have U and D, and this is the case to a proton. And this it's easy to do. You have the current coming here, the X becomes a U, and this current is a current that it's a weak current that couples to S and U, right? So this is a W. But if you want to do some structured quantities like the electromagnetic form factor, where this is a photon, and the photon couples to the quarks of the same flavor, UU, okay? Still axial, but it's quarks of the same flavor. This now vertex, of course, when you put it inside the contraction, it's a vertex that can close with itself. Okay, and this gives you disconnected contribution because this gives you the case where the two quarks that are one ingoing, the other outgoing, closes like this, okay, and couples with the nucleon. And these are, again, it's something extremely challenging to compute because now this is a correlation function. When you write it down, this is a correlation function where you need to correlate your 2-point functions with disconnected loops. And these are much more noisier data, even more challenging, because when you do now you have a chi-n, the interpolating field, the current, and which is, let's say, U bar U, gamma mu, and you have, again, interpolating field chi-n, you can see that one of these diagrams is that one, where you have basically chi-n, and the loop, where this closes. And you need to compute this correlation. So it's a correlation of a loop with that. You compute loops that are trace of the Dirac operator, you compute the nucleon, and you get this kind of diagrams, which you need to add to the connected contribution. And then this is what we refer to disconnected, connected, and you get this result, okay? I don't think this is matching. I don't know why I have it. Okay, this arrive at the end. Okay, but these again, it's other technology that one does, but it's possible to compute these results. Okay, these are anticipated before. An example are these form factors. You can get many of them, like the pseudo-scarred axe, but yeah, it's, then you have data points at different q square. You can do it at different energy. So you can put a momentum here in the nucleon, the other weak at rest. You have a momentum transfer. So if one of the nucleon is at rest, the other is a momentum, then the momentum goes the current, right? And so you have momentum transfer, and this is the form factor. And you can feed them and get results that are like these, and you can compare them to experiments. So you can see here, these are experimental results at low q square, and these are lattice results at low q square. Okay. Okay, with this, I covered the material. Now we can go back if you have questions, etc. Okay. So, yeah, 5 minutes of questions. Anybody? Yes. Yeah. Yeah. No, I mean, very often you get this. So what we consider so far are connected diagrams. Connected diagrams are very nice because are propagators of quark, okay? Are contraction of propagators quark propagated from a point to another. Okay. A very simple example, if you want to do it as an exercise, okay? Instead of considering a charge pion, let's not go to the 3-point function, it's difficult. But if you want to consider the interpolating field, if you instead of considering the interpolating field of a charge pion that is just u bar d gamma 5, put in a certain position x, you consider the interpolating field of the neutral pion, put in a certain position x. The neutral pion, you know that is u bar gamma 5u plus d bar gamma 5d plus, let's consider just the first term, u bar, okay? U bar gamma 5u. Put in a position x. Now work out the contractions. If you want to do a neutral pion on the lattice, although we have isospin symmetry, so the mass of the neutral pion is the same of the charged pion, if you work out this contraction, and you do the contraction of chi bar pi 0, put at a y, chi pi 0, put at an x, okay? You do with contraction of these. These, having the same quarks, u bar gamma 5, u at a y, both put at a y, and u bar gamma 5, u put at an x. If you do with contraction, these two pairs can either contract as u bar u at y and x and give you the standard connected diagram, okay? Or they can contract in these two pairs, right? And these two pairs here is the correlation between two disconnected loops, put one at x and one at y, because they're closing on themselves. And computing this correlation function, it's 1,000 times more challenging than computing this correlation function. Because this, it's beautiful. This is the correlation between disconnected quantities that are put into places. It's the trace. It's very, very challenging, this calculation, numerically. Okay? Because it's mainly due to the fact that the signal is very, very noisy, because how to show this? You can understand that the connected is yeah, okay, it's the answer, it's easy. While in the connected contribution, the correlation is done through the fermion fields, and this, it's very easy. The correlation here, it's not done through the fermion field, it's done through the vacuum. okay? Because you don't have any leading term that is the connector. All these one are correlated through gauge links that then they can decouple, etc., but are correlated to the vacuum. And the vacuum is something you're just sampling over the Monte Carlo simulation. So this is extremely challenging to sample properly. The vacuum, because it's the correlation that goes to the vacuum. Okay, so that's why it's very challenging. Okay, and the same it's here for these diagrams. Every structure you want to do of the nucleon, the structure, not the decays. So if you, all of this comes through currents that are of the same kind. So they can, right? So it's a current that couples through the vacuum with the nucleon. So this it's the current close to itself. So you can either couple to connect, so you can interact directly with the valence quarks, but interacting with the C, it's much more challenging. Okay, so that's okay. Okay, one more question? No? Okay, you have the slides. I wish a good continuation of the school. Thank you for listening.